Okay, missed class. This video will help with an introduction to acids and bases, the ionization of water, and the pH loop. First, let's be clear that you need to memorize your 7 strong acids yesterday. And this is color-coded because we want to pay close attention to the minus ions. We'll generalize and call it, instead of X minus, we'll call it A minus. These minus ions of the strong acids are important, and so this is a buy one get two list. You'll know the strong acids and you'll remember these minus ions. Likewise, the strong bases, of course, are your group 1 and group 2 hydroxides, your alkali hydroxides, which are very soluble, and your group 2 hydroxides, particularly the lower group 2 ions on the periodic table are more soluble. The top of the table, beryllium hydroxide and magnesium hydroxide, just not very soluble. Next, a quick bit of information to remind you about base 10 log facts. I want to be clear that you are well aware of the fact that 10 to the minus 3, or 1 times 10 to the minus 3, when you log that number you get a 3. 1 times 10 to the minus 10th, the log of that number will be a negative 10. We'll mostly be logging small numbers. Okay, but what if the number in front is not a 1? There's a lot on this slide, but let's take a look. Obviously, most of the time you will have your calculator, unless we're in a multiple choice question, and thankfully the answer options will be far enough apart to make our choice easy. Notice that the numbers out in front in the scientific notation cause the number after the decimal to change, and it's actually the times 10 to the minus that produces the number, the magnitude, in front of the decimal. And so it's important to note that there's an easy pattern. If it's times 10 to the minus 3, the log of that number, or the minus log of that number, would be 2 point something. 10 to the minus 6, the minus log of that number would give us a 5 point something. So 1 less than the exponent in the scientific notation. Now, just a quick piece about significant figures. Notice that this time I've left the beginning number all the same, and that results in a 0.34 every time. If I asked you how many significant figures are in this number, I think all of you would say just 2. That these are important to tell us that this is a small number, but not important to the significant figures. And so the 4.6 is causing the 0.34, the minus 3 is causing the 2, so in fact 2 significant figures, here they are, 2 significant figures. It's important to remember that in a logged number, only the numbers after the decimal are part of the significant figures. Alright, and you thought water was just water. Well, I'm sure you remember that the oxygen end of the water is the partially negative end of the water, and the hydrogen end of the water is the partially positive. This is a Greek symbol for delta. Lowercase delta, you're used to capital delta, and that in this context will mean partially. So when waters bump into each other, occasionally a hydrogen will stick and produce H3O with a plus charge, because just the hydrogen, just really the nucleus, stuck to the water, and left behind will be a hydroxide. We can pretend that this is also the same as water actually just breaking apart into H pluses and OH minuses. And while this is not actually what happens, we certainly will use this analogous to this situation. So we've got 2 reactions here, water bumping into itself, water decomposing. If we were to write an equilibrium expression for this, I would hope you could write this for this reaction, or you could write for this reaction, you could write that, K equal to. Note what's not in this expression. Notice that we have left water because it's a pure liquid, out of the equilibrium expression. So Kw, that stands for water, is equal to H plus times OH minus. We call this the auto or self-ionization of water, and it's the amount that actually proceeds forward is quite small. And you want to know how small. This small. That's 0.000001. That's a pretty small number. And so if we were going to calculate the Kw, then we can put 10 to the minus 7th in, square 10 to the minus 7th, and lo and behold, we get 10 to the minus 14th. This happens at 25 degrees. In this unit, most of what we will do will be at 25 degrees. Does this mean when you're drinking water, you're actually drinking acid and base? Well, not really, because these two amounts, H plus and OH minus, will be equal to each other. The water is considered neutral. Not neutral as in charge neutral, but neutral as in acid-base neutral. And the punchline is this. This ion product, or Kw, the equilibrium situation of water, is not true just for water, but for any and all aqueous solutions that we're going to be thinking about the equilibrium of H2O in equilibrium with its H ions and OH minus ions. So now let's think about the pH scale. I'm sure you've heard of this before, and that it comes from the fact that small quantities are a little bit inconvenient, dragging around 10 to the minus 5, 10 to the minus 4. So in order to make the numbers more convenient and easy to work with, we're going to take the minus log of the H plus concentration and call that pH. So this P actually means minus log. So the minus log of 10 to the minus 7th is actually 7, because the log of 10 to the minus 7 is negative 7, and we're going to change the sign to make our pH scale positive. If the solution were acidic, and we had more H pluses, 10 to the minus 4th instead of 10 to the minus 7th, the minus log of 10 to the minus 4 would give us a pH of 4. There's other P scales. Again, as I said, this P really means minus log of. POH, the minus log of the OH concentration. This is also on your formula sheet. And so for the pH 4 solution, where our H plus equals 10 to the minus 4th, because we learned about the equilibrium expression for all aqueous solutions, if we put in 10 to the minus 4th and we know what Kw is, we can solve for OH as being 10 to the minus 10th. So the POH minus log of 10 to the minus 10th will equal 10. Well, let's take a look at some common substances you're familiar with. Coffee is acidic with a pH of 5. Cola and vinegar, pH of 3-ish. You may have baking, well, certainly have baking soda at home. It's a little bit basic with a pH of 8. Notice when the pH is 8, the POH is 6. When the pH is 3, the POH is 11. You probably have some bleach at home with a pH of 12, and the POH will be 2. So there's a connection. It's well worth noting, and this also is on the formula sheet, that pH and POH will always add up to 14. This, of course, is at 25 degrees, which is mostly what we'll be working with. So this is what I like to call the pH loop. If you know any one of these 4 items, you can calculate the other. pH could allow you to calculate a POH. You could unlog to get the OH, or you could unlog the pH to get the H plus, and then apply this expression to solve for the OH minus. So we're going to ride the pH loop. Notice that when H plus is high, the pH is actually a low number, and the OH is actually very small, and the POH would be big. And then as the OH increases, larger blue area here, the H plus quantity is decreasing. And how these amounts of H plus and OH are related through the value of 14, which is our Kw, 10 to the minus 14. The pH being a log scale, sometimes you might say, oh, pH 1, pH 4, whatever. But if we make a comparison to a sports field that's 100-yard long, if we think of that as a pH of 1, meaning having lots of acid, that to change to a pH 4, the magnitude, it's orders of magnitude, of course, -1, -2, -3, and so we're down now to 3 inches out of 100 yards. So there's quite a bit of difference even between each one single pH unit.